Okay guys, today I will introduce a great simulator, RISC. RISC is a graphical processor simulator and assembly code editor. It is built for RISC-V instruction set architecture. Of course, is suitable for how assembly level code is executed on various microarchitectures. Okay, as we can see in the following window, here we have the menu bar. You can create a new program. You can load a program already exists in the directory of RISC. You can load a built-in example to test RISC, and you can save the program or save your current program in different file type. Finally, you can exit the whole application by clicking this button. Next, we have this toolbar. This toolbar contains all of the relevant actions for controlling the simulator. Also, we have 3 different tabs here in this area. We have editor tab, processor tab, and memory tab. Let us check each tab different. In the editor tab, we show 2 segments. Here we have left segment and right segment. On the left segment, you can write your assembly program, which is written using the RISC-V RV32I instruction set. Whenever any edits are performed in this program here in this area, and no syntax error are found, the assembly code will automatically be assembled and inserted into the simulator. Okay. On the right hand side, it's a second code view. We may view the assembled program either disassembled or in raw binary code. In between, we have a slide bar, blue slide bar. You can click on to make a breakpoint to check your sequence of executable code. Right. Let's try to write a simple code as we were discussed in the previous session. I will write some comment before by using hashtag. If you remember our last session, we discussed about how to add 2 variables in RISC-V. Suppose suppose we have A equal 5 and B equal 3. A is in register 1 and B in register X2. Okay, and you want to calculate C, which is equal to A plus B, and C is in register X3. Okay, first we need to initialize the value of 8 to 5. We use add immediate instruction. Add immediate instruction will add on the register X1, X0, the value it will be 5. You can add X0 to 5 and the result it will answer to destination register, which is X1. So this instruction will show you how to initialize the value of 8 to 5. Okay, as you can see on the right hand side, how your instruction is disassembled in RISC-V instruction set architecture. Okay, next instruction, add immediate, also to initialize the variable b to 3. I will use register number 2, X2, as a destination register. Initialize X2. I will add X0, which contain a value 0, to a constant value 3. As you can see on the right hand side, how is this instruction disassembled into RISC-V instruction set architecture. Okay, to add these two values, we need to use add instruction. The destination of this results, it will be stored in register X3, which contains the variable C. I will add X1 to X2. Okay, the summation of X1 and X2, it will stored in the register X3. Okay, on the right hand side, as you can see, we have 3 different columns. First column is called PC program counter. The second column is the memory address or instruction stored in the memory, how instruction is stored in the memory. Okay, how this instruction is stored in the memory. As you can see, program counter is initially start by 0. Since we use RISC-32I, program counter will increment it by 4. PC equal at each instruction executed. The second instruction will get PC equal PC plus 4. So the jumper here is equal to 4 byte, 0 to 4. Next instruction will be A. Next instruction, the PC will be 12. 12 in hexadecimal is C. Okay. This is how your assembly code executed in RISC-V instruction set. Now, let us check the second tab, which is processor tab. In the processor tab, is where RISC display its view of the currently selected processor. Already we have here the currently selected processor is single cycle RISC-V processor. You can change the type of processor by using the action button on the toolbar. You can select the processor. We have 4 types of processor using in RISC. You can use single cycle, you can use 5-stage processor. If you would apply pipelining in your processor architecture, you will use 5-stage processor. Another type 5-stage processor with hazard detection or with forwarding or hazard detection. Currently, I will use single cycle processor. This tab provides us several views about what your program can execute. Here we have registers. Here we have registers in RISC-V. As we know, in RISC-V we have 32 registers from X0 to X31. X0 is initialized or hardwired by 0 value. You cannot change this value. We have X1, X2, X3, etc., and so on. Each register here has an alias. You can refer to this register by an alias. X1 register address, X2 stack pointer, global pointer. We have temporary register T0, T1, T2 from X5 to X7, and save register as 0, S1 from X8 to X9, and address register. Also, we have here save register from X18 to X27, and so on. Okay. Here you can check the value of each register. You can check it by hexadecimal view display or binary, or you can check it by unsigned display. Unsigned, it means all positive integers, or signed if you have any negative integers, or ASCII character if you have a character value. I will keep it hexadecimal notation. Then you can see here a section about instruction memory, how your instruction is assigned to memory by its address. We have here address 0, address 4, according to PC counter, address 8, instruction fetch in memory. Each instruction is fetched to this address, and the stage, at each stage you will see this dot because we use single cycle RISC-V processor. Area, you can check the statistics of your program. Okay, we have various statistics based on the cycle count. Cycle count, how many cycles, instruction retired, current number of retired instruction. You can check CPI, cycles per instruction, IPC, instruction per cycle. Finally, we have here the output view. You can display any output or any value from your registers, of course, by using equal function. We use equal function to print an integer or any different data type value from any register. Okay. The third tab, memory tab. As you can see here, we have memory address, which is the PC program counter. At PC 0, at address 0, we have this instruction. Each instruction and memory address, the length of each instruction of memory address is 4 bytes. We have byte 1, byte 2, and byte 3. As you can see, 93 in hexadecimal is stored in byte 0, and 00 is stored in byte 1, 05 is stored in byte 2, finally 00 is stored in byte 3. Okay. Now let's try our code and to check what will happen in our registers. I will go to my toolbar in RISC, and you can click run action from here. Okay, your code is run, no errors. Go to processor tab and check what happened in your used registers. In register X1, we have value 5. In register X2, we have value number 3. The summation of X1 and X2, it will be stored in register number 3, which is 8. Okay. If you check the statistics of your current program, your program is used 3 cycles to execute, and we have here 3 instructions retired. The CPI of your code is 1 and IPC is 1. Okay. If you select a different processor architecture, let's try a different one, 5-stage processor, which allow us to use pipeline concept. Okay, pipeline concept. I will run our code. As you can see, your statistics is different from the previous processor type. Okay. What we can check from this process. Let's try by using these actions. I will go to my code in the first editor tab. I will try to reset our code to initially reset our PC counter to 0 and try at each clock cycle what will happen. I will press clock. If you can see here, first instruction it will be decode, the second one it will be fetch at the same time. This is a pipeline concept. You can check it also here from this table to see your stage. First instruction at cycle 0, instruction fetch, the operation is IF. At cycle 1, it will be decoded. At the same time, instruction number 2, it will be fetch. This concept is called pipeline. Okay? You can try all cycles by using in a single click by using this automatic cycle, using this action. You can check your stages here. 3 cycles. We have instruction fetch for the first instruction at cycle 0. At cycle 1, we have instruction decode, instruction fetch for second instruction, execute, memory, write back to register. As you can see, to execute this code in the current selected processor, you have 7 cycles. Let's check our statistics. We have 7 cycles. We have 3 instruction retired. The CPI is 2.33. Finally, the IPC is 0.429. Okay. If you want to print a value, the value of C, which is stored in register X3. Okay. You want to print value of C, which is in register X3. We will use a function call called eCall, but you have to know some tricks or tips to use this function call. First, you need to write my instructions here, and later I will discuss every single line. X0, X3. You need to store the value of X3 inside the register A0. Okay, because function call to apply the function eCall, it's only applied for register A0. Second, you need to set what type of print you want to do. I will use register or address 7, 0. I will set it to 1. 9. This line, it means you set A7 equal 1 which means to print will use equal to print an integer value which is stored in A0 register. Okay, guys. If you need to print a different type of values, you need to set A7 to different value. For instance, you can set it equal 2, equal 3, equal 4. Okay. After that, simply you write equal function. And now you can run your assembly code and check if the value of x3 is displayed on the output session in the processor tab. As you can see, in the output session, output tab or view, you can see the number 8, which is stored in the register x3, is displayed here. Okay? That's all what we need to learn in this tutorial or session. Thank you, guys.